Okay, so let's start our class. Can everyone see the screen?
Yes, sir.
Yes, sir.
Okay, so we have introduced the electromagnetic field tensor in the last few classes. I think we are discussing about the transformation of this tensor, and we have obtained a particular form for this. So let me just first write down that to start with the discussion. So electromagnetic field tensor. So we expressed it. So these are the contravariant components of the tensor F mu nu, and I told you how to obtain the covariant components of the same. And then I think, yeah, it's positive, yeah, Bz. That's Vy. This will be minus of Bz. 0. This will be Bx. And then By minus Vx. 0. So the electromagnetic field is completely described by this entity which we call electromagnetic field tensor. And when we refer to field, we refer to tensor, not separately to magnetic field. As you already know that electric field and magnetic fields are nothing but the components of this tensor. And we have also seen how it transforms from one inertial frame to other, and its component transform under Lorentz boost, and some elements can vanish in certain frames, whereas some zero terms can be, zero components can be also non-zero in some other frames. And you should also note that F mu nu cannot be boosted to 0, right? Because if F mu nu is 0 in one frame, it would be 0 in all frames, right? So it is not like that you have some non-zero components here and in some other frames it is 0. That is not possible. That I have already told you before, because there are some invariant quantities like f mu nu, f mu nu, and f mu nu, g mu nu, and they have to be invariant in all inertial frame. That's a requirement from special relativity. So there is no escape from it. But I should also warn you about this tensor, because I mean there is a lot of confusion, because if you go to different textbook, you may see different used. So I should tell you that you see there can be another equivalent form of the same tensor, because it is all about a second rank antisymmetric tensor. If I can have equivalent form which is equally valid, and there is no problem with this form, equivalent form. Same tensor, I can write it this way, changing the sign of each of the element or the component. I can write this to be minus ex by c, minus ey by c, minus ez by c, and this will be equally valid for the kind of transformation that we checked earlier. Sorry, this is ex plus x by c, ey by c, ez by c, 0. This will be minus of vz. This will be plus vz 0 minus bx minus of vyx. This form of f mu is equal correct. So if you choose this from that form, doesn't matter. You should also remember when you go from the contravariant component.
স্যার আপনার সাউন্ডটা কেটে যাচ্ছে।
Let me just check it. Why it is happening so? এখন আসছে ঠিকঠাক? Hello, can you hear me now?
হ্যাঁ এখন ঠিক আছে।
Okay, let me reconnect it again. ঠিক আছে এখন? Hello, can you hear me now?
হ্যাঁ।
Okay, ঠিক আছে, ঠিক আছে। So I was telling you that you can have both this form as a valid form of the electromagnetic field tensor. And if you want to know the covariant, see, if I take this to be my this to be the field tensor, for example, this one, right? So then in the contravariant in the covariant components of it, you can obtain it by just simply switching the sign of the space-time component and keeping the space part intact. And you don't need to change this part. You just change the sign of this time component. So that will give you the covariant components of f mu. Similarly, if you choose this form, again you have to just switch this sign of the space-time component, keeping this part intact, right? So again, if you go to Jackson's book, you will see that f mu nu, basically f mu nu in Jackson's book. Okay, let me write it again. In Jackson's book, it is like this: 0 minus x minus ey minus ez ex ey. Wait. So my ex ey, and then where is that? Ex ey and ez. This will be 0. This will be minus of bz by as bz 0 minus of vx minus of by. This will be bx and 0. Now I should tell you that this form, which is written in Jackson's book, is actually, these are Gaussian unit, right? So if you want to use this form, there is no problem. You should remember that your electric field and magnetic field has to be written in proper unit. Otherwise, if you want to use SI unit in some part of your calculation and Gaussian unit in some part of your calculation, that will be problematic. If you want to use this form, then you have to to relate them properly. So electric field in SI unit, you can see the appendix of Jackson's book. It is written there. E in SI unit, basically electric field divided square root of 4 pi epsilon naught in Gaussian unit. and B in SI, B magnetic field in SI unit, you have to multiply by mu0 by 4 pi. Right, these factors are not there in Gaussian unit. So B in Gaussian unit. And you see, again, I can choose also this form for the same, keeping this to be plus and this to be minus, and just changing the sign of all the special components as well. So, I mean, since this can be written in various forms, so that can be a source of confusion. So that's why I'm telling you this in the beginning, so that I don't get confused when referring to different textbooks. So I mean, it is the same electromagnetic field tensor which describes the electromagnetic field completely, but there are different ways to write it, right? So what I would suggest, just stick to one particular form, and that's really sufficient. You don't need to worry about how other forms are different. Fine. Well, so and we have learned how to transform this quantity from one frame to other. But our next goal is to actually develop the electrodynamics which we have learned earlier in the tensorial notation, so that we can write down them in 4-dimensional space-time, where the Maxwell's equation should be, in the 4-vector or this tensorial form. So how to do that? If you remember, the Maxwell's equations, they not only involve electric field and magnetic field, but also derivatives of them. So we need to know how the derivatives transform with different inertial frames. Unless we know that, we cannot really write down equations in the vector or tensor form. So let us first discuss how the derivatives of a quantity in 4-dimensional space-time can be written, and how those quantities will transform from one frame to other. So we are going to discuss about derivatives in this. And their transformation. Okay, so there could be different kind of derivative. As you know, in vector calculus, you have learned about gradient, divergence, curl, and so on. For the time being, I'm just talking about, say, gradient, so del operator. Like in 3D, this gradient operator, you write this vector operator, and this is basically these are 3 components, a vector, del operator. And what is the equivalent operator in 4 dimension? We call it box operator. You must have learned this while using different gauge condition, and you can write the Maxwell's equation in terms of potential. And in that case, you have some freedom called gauge freedom, by using which you can express the Maxwell's equations in terms of the electromagnetic potentials. তো তোমাদের কি গেজ ট্রান্সফরমেশন পড়ানো হয়েছে লাস্ট সেমিস্টারে? হ্যালো, ক্যান ইউ হিয়ার মি?
স্যার ক্লাসিক্যাল মেকানিক্সের সেকন্ডটা একটু পড়িয়েছিলেন, ইলেকট্রোডাইনামিক্সে হয়নি।
ওকে, ঠিক আছে, তাহলে আমি এটা যখন পড়াবো তার আগে একবার টাচ করে নেবো। ঠিক আছে, জানা থাকলো। Okay, let me just write down this gradient operator, which you call this box operator in 4 dimension. So basically, since we need to involve the time, the derivative with respect to time, so that's why let me write this x0, okay, del x1. So x0, x1, x2, x3, basically, these are the 3 spatial coordinates, x1, x2, x3, xy, z. Don't confuse with that one. X1, x2, x3 are basically x, y, z, and this is the times basically c dt, 1 by c del t. And so this quantity, this thing is whether that's a 4 vector or not. It has to be 4 vector, because this is in 3 dimension, this is 3 vector, right? And if this is a 4 vector, how that would transform? What kind of transformation? Contravariant vector or covariant vector? What is that? So you need to know that. right? So to understand this, let us start with a general I mean any vector. Let us write down the transformation of a contravariant vector. So when we have a contravariant vector, its components transform. This definition you must have learned this. A mu prime is what? Del x mu prime, del x mu prime, del x nu. We are the del x nu, mu and nu just two indices, and a nu. This is the transformation rule for a contravariant vector. I'm not talking about 4 vector. It could be 3 vector, it could be 4 vector, it could be any. But in this particular discussion, where we are discussing about things in 4-dimensional space-time, so there we must be dealing with 4 vectors, not 3 vectors or 6 vectors. We are talking about 4 vectors. Contravariant 4 vectors, they transform via the same rule. And if you remember, this thing is nothing but the Lorentz transformation matrix. If you write down that lambda mu nu, we shall check that lambda mu nu a nu. You can check it if you want. See, what is lambda mu nu? Lambda mu nu, lambda mu nu. I have just written this one, right? Del x mu prime, del x mu prime, del x nu. Okay. And what was x0 prime? If you remember, x0 prime. Maybe I wrote earlier capital X. Okay, don't confuse it. The same thing. Whenever I am using x0, x1, x2, x3, there is nothing but this capital X, the 4 vector. X0 prime, the time part is gamma x0 minus beta x1. I mean, if you write capital X, if you're comfortable with that, write all of them. It's capital X, doesn't matter. Beta x1, right? And if you calculate the different elements, you can see what is lambda 0, 0. If you calculate lambda 0, 0, this is del x0 prime with del x 0, right? Del x 0. And what is that? If I take a derivative, this is nothing but gamma. What is lambda 0, 1? This is del x 0 prime and del x 1, right? This is minus beta gamma. You can clearly see that these elements are coming up, right? What is lambda? What is lambda 0, 2? This will be del x 0 prime by del x2, which will be 0. What is lambda 0, 3, and so on. I mean, it's the same things. Del x 0 prime, del x3, which is 0. So if you calculate all the terms, I mean, this for this del x mu prime, del x nu, you will get each of the elements of the Lorentz transformation matrix. In our case, a mu prime is simply lambda mu nu a nu. And this is for the contravariant 4 vector, contravariant components of a 4 vector. What about the covariant components of a 4 vector? How do they transform? If I ask you, they transform like a mu prime. A mu prime is a contravariant component. A mu prime will be del x nu, tolai prime hobe, del x nu, del x mu prime, and then tolai hobe dutoi covariant a nu, right? Nu, this is mu, and so this will be basically lambda nu mu and a nu. So this one is for the covariant components, and this one is for the contravariant components of a 4 vector. Now, what was our goal? We wanted to know how basically the derivative, I mean this 4 gradient would transform, I mean under Lorentz transformation. That is we want to know. Let us see. We have also seen that if I have a tensor, that is again I can write down this field tensor which you have wrote earlier. Mu nu prime is what? This is again del x mu prime, del x alpha, del x nu prime, del x beta, and f alpha beta. And these are nothing but lambda mu alpha and lambda nu beta f alpha beta, right? We have also learned about this transformation. So all these are known things, how the 4 vectors and the, I mean 4 vectors are nothing but tensor of rank 1, and how a tensor of rank 2 transform. So these are known things to us. But our interest is how the gradients or the derivatives should transform. So let us do that. So del x mu prime, this is the derivative with respect to the contravariant components of a four vectors. We want to know how it transforms. So let us write this. We can write this to be del say x nu del x mu prime, and say I write del x nu del x nu. Look at this. I mean, if I ask you what kind of vector is this, if you look at the transformation law, I can write del x mu prime as del x mu prime into del x nu. This would cancel and you can have del x mu prime. So what kind of vector it look like? It's a contravariant 4 vector or covariant 4 vector?
Covariant.
Covariant, correct. So the derivative with respect to contravariant vector transform like a covariant vector, that you should remember, right? And that's why when I write del x mu, this is usually written as del mu. এটা লেখার কারণটাই হচ্ছে তলায় লিখছি দেখো del mu, কারণ এটা কিন্তু ডেরিভেটিভ with respect to contravariant components of the four vector, which transforms like a covariant, right? So this is the transformation is like a covariant vector. So that's why it is written del mu. And if you remember, del mu, I mean, if they are the covariant, I mean contravariant derivative transforms like a covariant vector. So this will be all positive, right? 1 by c. These are the different derivatives, right, with the time component, and then del x, del y, del z. I'm not writing them separately. Okay, just del operator. Okay, which are del x, del y, del. They will be positive, right? Because for the contravariant vector, all the components are positive. That's why these are positive. But here you see this is in the and subscript. So I mean this is the covariant quantity vector. And similarly, if I ask you what is the transformation of the derivative with respect to say, covariant components, I mean, if I write this way, del x mu prime, let us write this. If I write this will be again in the same fashion. I can write del x nu tolai and del x mu prime into del of del x nu. So what kind of transformation is this? Can I say something here? Is it a covariant, contravariant?
Contravariant.
How are you saying that? If you remember the contravariant, okay, let me write it side by side. That need to be clear. So you are saying that this would transform like a contravariant. Contravariant 4 vector transformation chilo a mu prime equal to del x mu prime del x nu a nu. Do they look same? একটা কোভ্যারিয়েন্ট হলে একটা কন্ট্রাভেরিয়েন্ট হবে, এটা অবভিয়াস টাইপের মনে হচ্ছে, বাট ক্যান ইউ সে দ্যাট দিস এন্ড দিস সেম? This quantity and this quantity, are they same or not? This quantity inside this bracket and this quantity over there, are they equal or unequal? Okay, let me just write down that whether they are equal or not. Del x mu prime equal to, for the timing, okay, let me write this, whether that's correct or not. Let us check that. Del x mu multiply, what do you get? You get del x nu equal to del x mu prime, del x mu prime. Is that correct or not? Because
Yes, sir.
the space
Four
time
vector
interval,
duto.
yeah, that is always correct right. It's just the interval between the, I mean, we have all done that the ds square is invariant, right? And this is nothing but ds square, dx nu, del x nu, or del x mu prime, del x mu prime. These are nothing but ds square. So in another frame it will be ds prime square, but they must have to be equal. So I can replace this by this quantity over there. So I can write del x mu prime, del x nu, del x nu. Then I can say, okay, right, then this transforms like a contravariant vector, contravariant 4 vectors. So that's why del x mu, del x, del x mu, what should I write? That equal to, since this transform like a contravariant 4 vector, that's why I write it's a superscript del mu. And remember, these are contravariant, covariant components. So the spatial components will be negative. So 1 by c del t, and then minus del y, minus del z. So minus of grad operator. So these are important. You should remember this, because when we shall write down Maxwell's equations, these will be used again and again. So you should remember this, the derivative with respect to covariant and contravariant components transform like the opposite, right? This transforms like a covariant, this transforms like a contravariant vector. And the derivative is a low range 4 vector, and we can also write del mu equal to 1 over c square, which we call box operator square. Just like Laplacian, we wrote, earlier we wrote this minus Laplacian square. Sometimes it is written as box square, right? So this is nothing but del mu, right? And okay, so now our goal will be to write down the equation that we are familiar with, like we have learned different equations in electrodynamics, like Maxwell's equations of continuity, or the equations in Maxwell's equation in terms of, say, scalar potential and vector potential under different gauge condition. So since I think you have told that this was not covered in your previous semester, so maybe I will touch upon this in my next class and then elaborate on this. For the time being, I will just mention you the equations, but I think we should derive it at least to know how they comes. Okay, so before that, let me start with the simplest equation, the equation of continuity. That's the simplest equation. So what is our goal? We want to write down the equation of continuity in terms of tensors or vectors, 4 vectors. Why? Because we know that the quantity which are involved in this equation are actually not a 3-dimensional quantity, although we use it for the sake of simplicity. But if you remember, what was the equation of continuity? It is basically a charge conservation. It tells you about charge conservation. If charge is flowing out from some volume, you have current, right? So the charge density is basically decreasing. If charge comes in, your charge density increases, but the total charge remains conserved. So it is just the statement of that the charge is always conserved, the equation of continuity. And since it involves the charge density and the current density, which we have learned in this course, that charge density and current density are not separate things. They are component of a single entity, which we call the charge density, current density 4 vector. So if you want to write down this equation, del rho del t, this is the equation of continuity, plus say divergence of J, this is the three current density equal to 0, right? This can be simply written in terms of the 4 current density, because if see, this is not difficult. You can see this, if I write this as 1 by c del t of rho c, which is nothing but the time component of the 4 current density, and these are simple divergence, I mean del x of jx plus del y of jy del z of jz equal to 0, and realizing that j mu is basically rho c jx jy jz, the four current density. And what kind of derivative is this? If you look at that, all of them are positive. You see, time derivative is positive, space part is positive. তাহলে এটা কি ধরনের ডেরিভেটিভ হবে? একটু আগে শিখলাম আমরা, কন্ট্রাভেরিয়েন্ট না কোভেরিয়েন্ট? কার রেসপেক্টে ডেরিভেটিভ হচ্ছে এটা? কন্ট্রাভেরিয়েন্ট, রাইট? এবং কন্ট্রাভেরিয়েন্ট কিভাবে লেখা হয়? তলায় লেখা হয়, এটা মনে রাখবে। তলায় লেখা হয় উল্টো, 1/c, ঠিকই বলেছো, del t del x del y কন্ট্রাভেরিয়েন্ট। তার মানে আমার ইকুয়েশনটা কি দাঁড়াবে? এটা কার ডেরিভেটিভ নেওয়া হচ্ছে? j মিউর, del mu j mu equal to 0. This is equation of continuity. And the beauty is that this equations will look much more compact. You see, of course you can see it's the same equation. I mean, what do I gain by doing this? The only gain is that, you see, when we work in 4-dimensional space-time, so your course is limited up to this, I mean, because you are only learning about the Maxwell's equation, but many things can be done in 4 dimensions. So if you want to do those calculations in 4 dimensions, it is easier to use, I mean, these tensorial equation, because they actually are expressing their real nature, right? Because rho and j are artificially seen as separate things. Like one thing is charge density, another thing is current density, but they are not separate things. They are component of the same thing. So if you compare it with this equation and this equation, the content wise they have the same thing, they have same meaning, but this looks much more compact because it is telling you a very simple thing, that the contravariant derivative of the 4 current density is 0, right? So in a 4-dimensional space-time, and in 3-dimensional space-time, you have to use a lot of language. Okay, if charge is flowing out from a volume, then if charge density, current is flowing out, charge is flowing out, density decreases, and of course the meaning remains same, but the language becomes simpler. That is the gain you get by going into 4 dimension, right? Because they are expressing their real nature, right? Okay, fine. And now I shall go to the Maxwell's equation. And Maxwell's equation, I think I told you that electric field, just like if I think this has nothing to do with the gauge transformation. I mean, electric field in electrostatics, what do we write? Electric field is written as what? Minus of grad phi, right? Electrostatics. But if you go to electrodynamics, you cannot write this anymore. You have to also involve the vector potential, right? Del A del T. This can be easily shown, right? Because curl of E and curl of E is not, I mean, divergence of E and divergence of B. But since divergence of B is 0, you can simply write it curl of A. So these are coupled, no, right? Electric field, magnetic field, they are, coupled, and the scalar potential phi and A, they actually are another 4 vector, which you call the 4 potential. So rather than writing them separately, actually, we shall see why we call them a 4 potential. A mu is basically phi by c, and then the 3 components of the vector potential, ax, ay, az, and this is 4 potential. So you don't need to think separately as scalar potential and vector potential. They are the same 4 potential, only the time component and the space component. So 4 potential for A mu. And we will relate these things, how we can obtain A mu from F mu nu, or how do we relate the different things. So in 3 dimension, I think you can use this relation to arrive at a set of equation which we call they are the Maxwell's equation, nothing but the Maxwell's equation, because you are basically expressing those equations in terms of phi and A, because E can be written this way and B can be written this way. So if you put these things in your Maxwell's equation, simplify them, and then you will get 2 equations, one in terms of phi, another in terms of A. Those are nothing but again Maxwell's equation. And because you see the real things which you deal in real situation is the electric field and magnetic field, and the potentials are basically construct. Basically, they are mathematical abstract quantity that we construct for our advantage, because we can easily obtain electric field and magnetic field from them, and it is easier to calculate scalar potential and vector potential for a given problem using different kind of symmetry. So that was the reason why potentials are used. We do not directly calculate electric field and magnetic field in most of the situation. This thing actually give us certain advantage, because you can incorporate certain condition in your formalism so that E and B are not changed. So phi and A can be in such a way B are not going to change, and that is called gauge freedom. I think Srikanth has already taught you that, so you already know about that. But again, I will repeat this in some other class. So phi and A can be tweaked in such a way that electric field and magnetic field are not going to change, and that is called gauge freedom. And there are different choices for that. So one can choose, for example, say divergence of A equal to 0, right? That is known as the Coulomb gauge. Again, there are certain advantage of a gauge that you can only infer by writing them in a proper way. Otherwise, if I am just saying that, it will not be comprehensible. So I will do that separately. So for the time being, I'm just telling you the most advantageous gauge is a Lorentz gauge. If you are working in relativity, Lorentz gauge is the most advantageous gauge. And if you use that gauge transformation, you can write down Maxwell's equation in terms of scalar potential and vector potential in the following way. So I'm just writing the equation. These equations may be familiar to you. Just tell me whether you have seen this earlier or not. I hope you have seen this. This box square phi is equal to minus rho over epsilon 0. Of course, rho is a function of space and time. This is not a constant, right? Similarly, phi is also a function of phi RT, rho RT. I'm not saying that. And this is not Laplacian. We call it D'Alembertian. Right? This is J. So this is a vector. This is a vector, and they are function of space and time. Right? These are the Maxwell's equation under Lorentz gauge. Right? And here you have this. Box square is Laplacian square minus 1 by just the opposite of that, del mu, with a minus sign over that. So these two equations are nothing but Maxwell's equation, right? In a general setting, if you are working in 4 dimension, choosing a Lorentz gauge is the most advantageous, because they treat phi and A in the same footing. You can see space and time both are involved. Coulomb gauge has certain disadvantage because it violates causality. I will discuss that. So here phi and A, you can see phi and A are expressing 2 equations, but again you see phi and A are nothing but the time component and the space component of 4 potential, right? And the source term are here. You can see this is the time component of nothing but the time component of the 4 current density. These are the space component of the 4 current density. On the right hand side, left hand side, you have 4 potential. The box square of the 4 potential. On the right hand side, you have something multiplied, some constant multiplied by the 4 current density. But how do we write that equation? Let us simplify that. Okay. So okay, let me just write on the first equation. So first equation was Laplacian of box square of phi equal to minus charge density divided by epsilon naught. So I'm simplifying this way. Laplacian, Laplacian of phi minus 1 by c square equal to minus rho. So as I told you, noting that the quantities on the left hand side and right hand side are the components of 4 potential and 4 current density, you can simplify this further as, say, if I take a minus sign common from here, so I will write say minus of 1 by c square. Let me write it at phi by c. If I write it phi by c, okay, I have to do something. phi by c. So I am dividing by c, each term by c, Laplacian of say phi by c. I will also write divide by c on the right hand side. So what I will do, rho minus of rho by epsilon 0 c. Minus will be cancelled from both sides, right? And if you look carefully, you see epsilon 0 c can be also written as, this can be written as rho mu 0 c, because mu 0 epsilon 0 is 1 by c square, right? Mu 0 c, mu 0 rho c, right? This one. And if you see that rho c, what is rho c? Rho c is nothing but the rho c is what? This is mu 0 j0, the time component of the 4 current density, mu 0 j0. Similarly, I mean, it's a very similar thing. If I simplify the other equation, box square of the vector potential A equal to minus of mu naught J current density, I can again write down this again the same fashion, this A minus 1 by C square del T square A equal to minus of mu 0 J, right? And again, if I take a minus common from this side, I can write 1 by c square del square del t square a minus Laplacian a equal to Laplacian square, Laplacian, minus of mu, no, plus, minus sign will be cancelled, mu 0 j. So you have three equations, right? Each for x component, y component, and z component, which I am not writing. It's trivial to write that. I mean, write one equation for x component, another for y component, another for z component, and you can easily realize that these are nothing but the same set of equation. If you look at this equation, you see this is 1 by c square del t square of the time component of the 4 potential, and then Laplacian of the time component of the 4 potential equal to mu 0 times j0. You see, if I write down this equation in terms of the x component, this will be 1 by c square del t square of the x component minus Laplacian of x component equal to mu 0 jx. Similarly for y component and z component, so they look pretty similar. And if you now realize that mu is mu, what is mu? We already wrote that mu is phi by c x a y a z, or I think I'm writing them together, a, this is, and we also know what is del mu, right? Del mu 1 by c square del t square minus this. You see the same thing is operated on each of the equation, right? Same thing, right? On the right hand side, left hand side, we have basically del mu a, what, mu or nu? Mu 0. You see the operator is same. I mean, del mu operated in each. There are 4 equations. On each equation, in each equation on the left hand side, we are operating the same thing, del mu, but the components are different. For the first equation, it is a0, second is a1, third is a2, and fourth is a4. Sorry, a3. So that's why it should be a nu. And keeping with this, you see on the right hand side, if I have a time component, I get the time component of current density. If I have a space component of x component, we have x component of the current density. This should be mu 0 j nu, mu 0 j nu. So these two are mu, these two are nu. So be careful about that. So this is the compact form of the Maxwell's equation when we write down them in terms of the 4 potential and the 4 current. Okay, so what next? Okay, we have many other equations which you have to write down. Again, what I am telling you, I mean, these are not mathematical jugglery. This is something more than that. But for the time being, you may feel that these are nothing but the same equation, but we are writing them in terms of mu and nu. Okay, partly true, because anyway, we are not using them rigorously for further calculations. Basically, we are writing them in this notation. Well, so the next equation, I think maybe how much time I have? Only 10 minutes. No, it's not sufficient. Okay, maybe I can introduce and then stop. Maybe I can continue from today's class in the next class. Okay, so you see, I told you that the electric field and magnetic field, they are connected with the potentials, right? So how are they connected? If I this electric field E is connected to the scalar potential and vector potential in this way in electrodynamics. So if you know phi and A, which are the four components of the four potential, we can calculate electric field separately, I mean X component, Y component, and Z component. But why we should do that? Because we have learned about the field tensor, right? So we should not think about electric field and magnetic field separately again and again. We should be familiar to use, I mean, we should be confident to use this quantity, this field tensor, right? Because that represents all the components of electric field and magnetic field. So basically, this is rewriting the same set of equation in a different way. So B equal to curl of A and E equal to this, right? So our goal is to, you can simplify this also further. If you want to, you can simplify. This is what this is. I mean, all the X component. This is minus X cap del and phi del X, Y cap del phi del Y, Z cap del phi del Z, and again similarly del T of X plus del T of AY del T of AZ. And this has to be written as X cap, Y cap, Z cap in a matrix form. You can write del X, del Y, del Z, and separate out each of the components. And if you try to check or relate these things with the different components of F mu nu, it is interesting to see that actually there exists a very simple and elegant relationship between the field tensor and the four potential. What is that? Okay, this may be again known to you, because if you are using some, you have already taken some course in classical field theory, these are very, I mean, common things, and they must have to be used. So F mu nu is what? Del mu A nu and del nu A mu. Similarly, the covariant components of the field tensor can be written as del mu A nu is del mu A nu del nu A mu. This is one way of writing. Again, I told you that M mu nu can have different forms. So based on what form you have chosen, sometime you may have to also write F mu nu is del nu A mu del mu A nu. And that is not surprising, because that is obtained by switching the sign of each of the component. You see, this is nothing but the, if you take minus outside of this, you'll get this one. So based on which particular form you have chosen, you may have to write down the field tensor, I mean covariant or contravariant components of the field tensor in terms of the four potential in this two different way. So this will be again the opposite, del nu A mu minus del mu A nu. Anyway, my goal is not to confuse you, but to clarify you that, I mean, you should be careful. I mean, what kind of form you have chosen for F mu nu. It is not like that you can write whatever you want. No, that's not my point. My point is that once you choose your F mu nu, you have to stick to a particular notation. So suppose we want to stick to this notation, because this is a bit easier to remember, because I mean mu nu starts with mu nu, so mu nu and nu mu. Just switch the order. Here it is just opposite. Mu nu starts with mu mu and mu nu. It doesn't matter. I mean, it's up to you. I'm not prescribing any particular notation. It's up to you. So we shall stick to a particular one. I will stick to this one. That's my choice. Your choice could be different. But as long as you are, I mean, obtaining correct result, I have no problem with that. But if you mess up things, I mean, by choosing one thing or one notation and the other thing in other notation, then of course the things will be not correct, right? So should be careful about this fact. This can be easily shown. I mean, if you see what is F mu nu and what is A nu, I mean, again, you can prove it. I mean, but I mean, there is no point in proving that, because you see, you know what is Ex. What is Ex, right? That you know. Ex is what? You can write down what is Ex. Electric field is the X component of this thing, minus of del phi del X minus of del Ax del T, right? Similarly, Ey will be minus del phi del Y minus del Ay del T. And similarly, Ez will be minus del phi del Z del T. And break this into X cap, Y cap, Z cap, and del Z X, Ay, Az. And if you check I mean, this is not a proof. I mean, this is just we are inferring that A mu and F mu nu are connected via this relationship. So once you know the four potential in a given problem, you can easily calculate the field. I mean, problem, because when we know scalar potential and the vector potential, we can calculate the electric field and magnetic field. We are only changing our language, and the underlying physics is same. Okay, scalar potential we are obtaining. Earlier we were obtaining electric field and magnetic field from the scalar and vector potential separately. But now only the advantage is that we are not treating them as separate entity. We are only interested in knowing the four potential. So once you know the four potential in a given today, there is not much time left, 5 মিনিট হবে না, আমরা কালকে এটাকে কন্টিনিউ করি ডিসকাশনটা। আর এরপরে যেটা বাকি রইলো সেটা হচ্ছে ইলেকট্রোডাইনামিক্স, মানে আমাদের আর কি কি আছে, আর যা যা ইকুয়েশন রয়েছে সেগুলোকে আমরা
স্যার শোনা যাচ্ছে না।